All right, questions? So far, the only thing that you're required to know is that exponentials are bigger than polynomials and polynomials are bigger than logarithms. Okay. There's our list over there of our review of discrete math, which I'll say a few things now, but then we'll kind of do things as we need them, especially for a few people that are in discrete math right now. Sound like fun? Okay, so remember the name of the game is we have some model of computation and we want to prove exactly what are the things that you can do. So the goal is proof in this class. This is supposed to be your class where we prove things. And we're talking about a math proof. So, review of math proofs. Yeah, Rahul?
How does proofs help us?
You want to know something with certainty.
So say I can prove a certain problem works.
Yeah.
With that knowledge, is the goal just to say, okay, the computer can do it, or I know that the computer can do it?
Right, the goal is to know something. So what do physics people do? They run lots of experiments and they say with 99% certainty this is true, right? Or like the gravitational constant is this to 10 decimal places with this amount of certainty because we've run these many different experiments, right? Or relativity is true over all the experiments we've done, but you may have missed something, right? There's no proof that it's correct. Or in in most of the other sciences, they don't do proofs, they do experiments, right? They verify things. So what would it mean if I said this sorting algorithm is correct? Right? So say, merge sort. How do we know that merge sort is correct? You run the code on some inputs and it sorts them correctly. Is that how we know? That's that's a dummy check. You want to make sure you don't have any. So you can check your code. So say check or test your code. That's one thing that's good to do, but that doesn't really prove that it's always going to be correct. So we want to prove the algorithm is correct. And why do we want to prove that the algorithm is always correct? Because we can. Right? I mean, if you can do it, you should. That's the difference between math and experimental science. Same thing with factoring. Like, I want to know with certainty that factoring's hard, that somebody's not going to come up with a clever algorithm someday and steal all my credit card information. That's the goal. I mean, if you can do it. Anybody else have any thoughts there? Any math majors in the class? Nobody? Just me? Okay, so there's our list of proofs over there. Basic proof techniques: induction, contradiction, and construction. We could go through a classic example of one of those if you guys want. Just to review. Anybody want to? All right, which one? Who votes for induction? Who votes for induction's hardest? Who votes for contradiction? Who votes for them all? We don't have time for them all. All right, let's start with induction. So the first chapter of the book, at least the second version of the book that I have, reviews this types of stuff and gives some examples. So you should read it because you should read it. Okay, so one classic thing that you can do with induction is, so what's the basic thing you can do? So can prove something is true for every integer. So that's what you can prove. Or for every integer greater than some value, or whatever. So one thing that you can prove, for example, is the sum of the first n integers is what? You guys should have this memorized.
Say n times n plus 1 over 2.
N times n plus 1 over 2. That's correct.
Yep.
And if you didn't remember it, you could try to prove it. And if the proof doesn't work, then you're wrong. Okay, so why do you know this is true? You could try out some small values of n and verify that it's correct, but that wouldn't prove that it's going to be correct forever, for every n. So you do your induction proof. Induction proof always has two parts, base case and the inductive step. So the base case is you just verify it's true for the smallest value of n, 1. So n equal 1, you have this side of the equation is what? I equals 1 up to 1 of I, so that's just 1. This side of the equation is just 1 if you're starting with n equal 1. This side of the equation is 1 times 2 over 2. That's correct. If you want to, you could do your base case for n equals 2 as well. Just to get a feeling for what's going on. Here you have I equals 1 up to 2 of I. So you have 1 plus 2. Then on this side, you have 2 times 3 over 2. And you simplify, and those are correct as well. You can keep verifying for more base cases if you want, but that doesn't prove that it's always going to be true. And if you claim that on a test, you're wrong. So don't claim that on a test. All right, so then we have our inductive step. That's the second part of an induction proof. So the way the inductive step is, you know that it's true for, say, n equals 1 and n equals 2, and use that fact to prove that it must be true for the next. So you assume true up to n, and use that to show it's true for n plus 1. Okay, so we claim that this equation is true up to n, and now we want to see how we can use that to show that it's true for n plus 1. Then the value at n plus 1 is equal to this. The right-hand side is equal to this. We just need to make sure that they're equal to the same. So we'll factor this n plus 1 out of both sides. And then you have 1 plus n over 2. We want to manipulate it so it looks like this. So we'll take this 1 and make that a 2 over 2. We don't make it look like that, so we'll combine this 2 over 2 and this n over 2. It's the same denominator, so you can write it like that. And those are the same. Okay, so how does induction go? You want to show it's true for all values of n. Verify some small values of n. Really, you only have to verify 1, but we verified 2 just for fun. Then, if you know it's true up to some particular n, show that it'll work also for n plus 1. And when you do that, you use the fact that you know that it's true up to the lower value. So then what happens is we know it's true for 2. So the manipulations we did here show that if it's true for 2, it's going to be true for 3. And since it's true for 3, it's going to be true for 4, and so on. So the main work, the base case is just you verify it. That's not hard. The induction step is you set up the equation for n plus 1, You break it down somehow so that the equation for n is in there. Use the equation, the assumption, and then it's just algebra to move things around to make them the same. So if you can't do algebra, you can't do induction. That's true. You need to be able to do algebra. And if you need to practice your algebra, then get an algebra textbook and do the odd exercises. All right. Say something to your neighbor about induction. Do it. Go.
You're good at induction, aren't you? I'm out to go over it again.
I always forget the order, and then I get stuck in this.
I'll let the rock my brain hasn't been used for I'm getting back. Sorry.
All right, questions about induction? Rahul?
What if the base case doesn't work?
Then your equation's wrong. Or you need to start with a larger value of n. So it could be the case, the question is what if the base case doesn't work? So it could be the case that it's going to be true for all, this is for all, people are okay with the for all symbol. If it could be that it's true for all n greater than or equal to 11. But it just doesn't work for smaller n. Then you would start your base case at 11. But if your base case never works, then your equation's wrong. Right? I mean, if I tried to prove that this is n plus 2 here, it wouldn't work out.
And what if it's the other way around? Like for, say for n equals 1 or 2, it works, and then something for n equals 3 doesn't work.
Then your induction step won't work. So it could be that it works for small values of n, but then it stops working at some point. If that's true, if it does stop working, then the induction step is just not going to work out. You can try it and it just won't work out.
So does that mean my equation is wrong?
Right.
It means
Right. I mean, this is if this works, the equation's true. It'll work for all values of n. Other questions? Yeah.
Does this mean the inputs are always related from one input to another?
So when you do induction, you're proving that some statement is true for all values of n greater than at least something. So you're proving it about integers.
If we are proving for odd numbers,
You could prove it for all odd n. Yeah, you could have a statement like that.
so there must be some relation between. one
Yeah,
and
there's some pattern of the values of n. So you could prove it for all
five.
odd n greater than or equal to 11. And then your induction step would say, so suppose it's true up to 2n plus 1. That's an odd number. Then you would prove it for 2n plus 3. And things would have to work out so that it's true. Other questions? Let's mention homework. So